Okay, so hope you had a chance to work this out, right? So let's solve it together. So we need to find the electric field here, right? So when you get a question like this, the first question you should ask is, so let's try to break it down, right? So first thing I would like to ask is, okay, so this is the shape, and I can think of, since it's a continuous charge distribution, I can think of this whole arc as formed of a lot of, small segments, right? Now, each of those segments will have some electric field here, and the total field would be the vector sum of all of them, right? So what will the first question we should ask is, what will the final result look like, right? What will be its direction, right? So let's say I take let's say some random segment here, right? Now what will be the field due to charge in this segment? It'll exert a force along this line, right? So if there was and the field would be in this direction, right? When you say field in this direction, what it means is if I were to put a test charge here, the force on the test charge would be in this direction, right? And I can find one more point here again. If I draw the line here like this, right? The field due to this would be in this direction, right? Now it seems like a little complicated problem because every single segment has a field in different directions. So how do we add it up? They are not in the same direction. But there is one thing here, right? Always, so in these questions, first thing is look for symmetry, right? Which we can use to simplify. So here the symmetry is this. If I take this charge, this segment here, and I take a corresponding segment here, right? What will happen? This segment is exerting a electric field in this direction, and this will have an electric field which should be in this direction, right? So now I have this one and this one, right? And I'll just make it equal length, so it shouldn't look like they are the same length, right? Now this electric field, right? This arrow, the lower one, right? This electric field will have two components. One component is along this, right? This is the horizontal component, and this is the vertical component. Similarly, the one due to this one, the red one, would again have a horizontal component, right? And it would have a vertical component, right? Let me make sure I'm drawing it a little more carefully, right? They're both of the same length. Okay. Now what happens? Now we can see this and this, the vertical components are opposing each other. They would cancel. So this would cancel, these two would cancel. But the horizontal, they are going to all add up, right? So this is the key. For each particular segment that we take, we need to find the electric field like we found for this red one here, and find only its horizontal component and then add up for each of those. Because the vertical components for this one, this will cancel the vertical of this one. For this particular thing, there will be a corresponding segment here, right? Which would cancel the vertical component of the field of this one. Any segment you take, because it's symmetric about this line, because of symmetry, for any segment there is a corresponding segment which would cancel its vertical electric component of the electric field. Therefore, we have to only look at the horizontal component of the electric field. Now let's do that. Now it's a simple problem. So I'll draw it separately here, right? So this is the charge distribution. This is the center, right? This distance is r. This is r, right? This is bisecting the angle. Now what I'll do is I'll take one segment, right? Which is, let us say, at an angle, say phi. This angle is phi, and this segment is subtending. This small segment is subtending an angle here. This angle I'm calling d phi. D phi, what is d phi? D phi means small increase in phi, right? Whenever we use this word d, dx means small increase in x. D phi is small increase in phi, angle phi, right? Now I'll find the charge due to this. The electric field due to this at this particular point, and then we'll take, let's say that this one will have a field in this direction. I will take only its horizontal component. Okay. Now what will be this field? Let me call it dE. Why dE? Because it is the field due to dQ. This charge here, I'm going to call it dQ. Okay. dQ is the charge due to on this small segment. So let's do that. So what will be dE? dE would be K charge upon distance square. K dQ upon distance square. What is the distance? Distance is capital R. Right? capital R. Okay, what is dq now? There's one more thing we need to understand. What is dq? dq is the charge on this segment. What is that? The total charges, okay, so the charge distribution, the charge per unit length is lambda. So charge for any segment is lambda into that length. Lambda is equal to charge upon length. So charge on any segment would be lambda into the length. Okay. So we can now say that dq would be equal to lambda into what? Into this length. This length. What is this length? Let's call it dl. Right? What is this length? This length is nothing but r into angle. Remember, angle is nothing but, what is angle? Angle is nothing but arc upon radius. Angle is equal to arc upon radius. Okay, which means arc length is equal to angle into radius. So we can say that arc length is equal to dq would be equal to lambda into angle. What is angle? d phi. So angle is going to be d phi into radius r. Now it will be somewhat easier. So now I can write my dE as dE would be, this would be k into dq, which would be lambda into r into d phi, right, divided by r square. Right? And what is the direction of this field? It is in this direction, right? But I want the horizontal component. What is the horizontal component? Trigonometry, right? If this angle is theta, this is the vertically opposite angle. This is a straight line, right? And this is a straight line, right? This line is straight line. So this angle is going to be phi, right? If I want the adjacent component of d, what will be? It will be d cos phi, right? So what I want is now, so we'll say dE cos phi, right, would be nothing but equal to k lambda r upon r square into cos phi into d phi, right? And here this r and 1 and this r and this 1 power will cancel. So now I have d cos phi is equal to k lambda by r into cos phi d phi. And if I want the total field, I have to now add up the horizontal components because of the field because of each of those small segments. So that would be, so total field is going to be nothing but integral dE cos phi, which should be integral k lambda by r cos phi d phi, and the limit of phi is from where to where? This whole angle is theta, right? So this is going to be plus theta by 2 and this would be minus theta by 2, right? So it would go from minus theta by 2 to plus theta by 2. Okay, I'm saying this is the lower limit is minus theta by 2, upper limit is plus theta by 2. Right? So now we can write this as this is equal to k lambda by r. It's a constant, take it outside. So k lambda by r, and this is going to be integral of cos phi d phi. Integral cos phi d phi. And the limit would be minus theta by 2 to plus theta by 2. And what is the integral of cos phi? It is sin phi. Differential of sin phi is cos phi. So this would be nothing but k lambda by r sin phi, and this would be from theta by 2 to minus theta by 2, and this would be k lambda by r into, put the values there, so it will be sin theta by 2 minus minus theta by 2. And what is sine of minus of some angle? It is minus of that, minus of sine of that angle, right? So sine of minus theta by 2 will be nothing but minus sine theta by 2. So and that minus and this minus will get cancelled. So we'll have sine theta by 2 plus sine theta by 2. That will be 2 sine theta by 2. So this would be 2. I'll bring it here. So we'll say 2 k lambda upon r into sine theta by 2. This is going to be the electric field total. Right? Okay. Now if somebody asks you what's the direction? Direction is going to be in the horizontal direction. Right? Now I'm just giving you E, but if you have to use a vector notation, I could have chosen this as the x-axis, this as the y-axis. In which case, if it is along this direction, if this is the positive x-axis, then this will become this into minus I cap. Okay? The total field, electric field vector would be this value magnitude into minus I cap, right? So that's how we find the electric field. Thank you.